You're muted, Russ.
I realized, yes. So I said, hi, everybody. We do have a breakout today. So if you go ahead and click the first cell of the notebook and queue it up. Ironically, we're provisioning the machine just to get the rotation matrix class, basically, but it's a little overkill. All right, 2:35. So welcome back. So last time we started our exploration of geometric perception, which I distinguished from deep perception as really being, reasoning about the geometry and kinematics of objects, especially using point clouds last time, which I argued was one of the sort of primary sources of information we get out of depth cameras. And the setup was basically that, we had so far assumed a perception oracle that could tell us where the object was in the world. We wanted to stop doing that and stop using these cheat ports and start using the camera outputs instead. And remember, we have both the RGB images coming out, but we primarily talked about using the depth. In fact, we didn't talk at all about using RGB last time, really just working with the depth. And I showed you a few point clouds from, how we can simulate point clouds and render point clouds. And I hope that made at least one impression here, which is that there's a lot of problems with the point clouds, even in the perfect simulated world. If I put a camera in a particular location and it's just looking at the object from one angle, then it's only going to see a part of the object. So there's a lot of point cloud algorithms that we could explore that really almost implicitly assume that you have all the entire point cloud and you're matching, really matching point clouds. But we need to talk more about partial views and then messy, noisy point clouds. So the goal for today is to talk about messy point clouds. We're going to basically be doing the robust version of what we did last time and start thinking about the particular types of noise we get, where they come from, how we might model them in a toy system, and then some of the algorithmic approaches to being more robust to them. So one of the particular types of errors we tend to get a lot of are dropouts, especially around the edges of objects or in reflective objects. We also get some outliers where you get false returns. Something might bounce off something like this and return a depth from some other part of the scene in the pixel that was really associated with a nearby object. So, dropouts and outliers are going to be part of the topic today. Okay, so let me switch to the whiteboard. I'm going to try to be better about watching the chat today, so feel free to use it. Okay, so I'd like to talk about robust point cloud registration. Okay, so we're going to build on some of the equations that we got to last time. So I'm going to put them up again for you just to make sure we're grounded here. So we thought about last time as point cloud registration as sort of as a least squares inverse kinematics problem. Inverse kinematics is just IK for me, right? And we talked about the notation was our model points. MI, oops, it's a lowercase I. And our scene points. SI, and they have positions in the world using our good old spatial notation, monogram notation, like this. In particular, the model points we think of as being given in the object's frame. And the camera points, or the scene points, I'm okay accepting them in the world frame, because if we know where our camera is or we have a transformation, we can go through a couple steps, the projection matrix of the camera and then the extrinsics of the camera to localize it in the world. But for the purposes of our discussion so far, we're saying it's okay to just work in the world coordinates. If you're a mobile robot, you might do everything in the robot coordinates instead of the absolute world coordinates. But as long as you put them both, try to put them both into a common frame, all is well. And our goal was to estimate the object's pose in the world. I don't write the W, it's implied, right? And key to that was the idea of correspondences. Trying to figure out which of the points in point cloud 1, so, in point cloud A correspond with which points in point cloud B. You could argue that that's maybe the heart of the perception problem. We used our notation that we said Cij says that scene point I matches model point J. Cool so far, yeah? All good? Now, the main algorithm we talked about last time was the iterative closest point algorithm, which broke up the problem into 2 steps. So the first case 1 was if we have known correspondences, or we've locked in some guess of the correspondences, where we could then write the optimization as trying to find some pose X. And I'll use the notation in SE3. That's just a way to say it's a valid pose. This is the special Euclidean group for 3 dimensions. I was trying to avoid that notation, but I ended up using it. It's the least characters, and I ended up using it a bunch in the notes. So that just means it's a valid, it's any 3D position, but it's a valid rotation matrix hiding inside there. Okay, and then now I just have to find that X so that it makes my corresponding model points transformed into the world frame match the scene points that are already in the scene frame. And I loop over the scene points in the way I've written it so far, the number of scene points. Now that choice is actually a little bit arbitrary. I could have written the whole thing, for instance, in the camera's frame, and try and put the flipped the transform to the other side and tried to correspond model points with scene points. One of the reasons I made this choice last time was because, and this time is because of that half mustard bottle. So I think for a lot of our applications, it becomes, it's sort of reasonable to say, I've got scene points for my model points, but not all model points are going to have a valid scene point. But as we see, as we zoom out a little bit, and if we have a table or we have other objects or whatever, that assumption is not going to be good either, and we're going to have to be able to have a richer notion of correspondence. But still, this gets us started. Okay. So what does that optimization look like, right? So when we go to actually type it in or make it more concrete, we wrote it as this. We're going to minimize over some position. So let me write this very explicitly here. Position in R3 and rotation, a matrix in R3 by 3. We're going to look over all of the 3 by 3 matrices. But then in order to make this true, which I haven't accomplished with this, I need to add the additional constraints that R transpose R is the, that R transpose is the inverse, and the determinant of R equal to 1. So we're going to be thinking about how do we generalize that to richer notions of correspondence and richer notions of outlier rejection in a minute. So I hope that at least sits as familiar. The notes did get filled in. I'm sorry they weren't there on Thursday. And honestly, I have to, there'll be a time in the semester where they're not there. I mean, I'm going to do my very, very best to get as far as the term, but we're laying the track down in front of the train here. And this is, it's not that there's another textbook that I could just pull from or something like this. We're putting down material for the first time, and I'm doing my best. Okay, so good. So I just basically said last time there's a magical SVD solution. Let me zoom in just a little bit more because there's at least one super key idea that we're going to build on here. Which the first one is, I wrote this here as having both position and rotation. Now, the reason SVD becomes magical in this case is because actually you can separate position and rotation and solve them independently. Okay, and there's a mathematical way to see it, and then there's a physical way to see it. So let me do the physical one first. The physical one is, the basic idea is, how do you make your problem depend on rotation but invariant to translations? Well, you do relative translations. Okay, so relative positions are invariant to P. Okay, so if I have my my object, I just want something that's not symmetric and has a bunch of points. If I'm working with the position of those points in the absolute frame, then that's going to depend on both pose and both the position and orientation. If I could pick some important, let's just say this one's really important. Okay, and then I did the entire, all of my, if I wrote down sort of only the positions as relative positions relative to that one point. Okay, then to some extent that point captures all the position information, and the numbers you're getting out for the other values only depend on rotation. Okay, now this would be a little suspect. We don't do this exactly because who knows if that particular point showed up, if this particular point shows up the moment we have our algorithm. So there's a better solution for the point that we do relative. And actually, like I said, it comes right out of the calculus too. But so what we end up doing is we make a canonical point. So the central point. Let me write it as M bar and S bar are sort of central points. You could think of that as central, or they're almost equivalent to like the center of mass of the point cloud. Okay, but if the mass is all one for all the particles. Okay, so the position of this point in like the similar to a center of mass is I'm going to sum over all the scene points, and it's going to just be the average of those scene points. NSPSI. And similarly, this in the object frame is going to be a sum over I of the M's. but I have to be a little careful. I want to sum over the ones that, the m's that have a correspondence, okay? So make sure you observe that CI there. And then because of that, I'm still summing over only NS of them. So you could think about what that means geometrically. You know, that's going to be some point sort of at the center of my object, right? Some center of mass kind of a point. One for the scene points, and then one for the center of mass of my model points, the ones that have correspondences. Okay, and then the magic is that if I write things in those coordinates, then everything becomes just a function of the rotation matrix. That's an equivalent optimization with the rotations, with the translations removed.
By the way, Russ, there's a question on the chat from Anubhav.
Yeah, see, I said I was going to watch it. Oh, awesome. Okay, so yes, all this stuff about SE3, that looks right. Just rotation is SO3, SE3 should have translation as well, exactly right. SE3 is pose, good. Can the minimization over R instead be a minimization over Euler angles? Typically, we don't do the Euler angle version. We can do the quaternion version. They still have a constraint. The Euler angle version, I think, doesn't have a great form. Not one that I know, and might be subject to the singularities and the like. Yeah, the mapping from Euler angles to quaternions goes through sines and cosines, and would introduce, at least naively, would introduce some gross terms in our optimization. It's a good question. Okay, so now this this problem is the problem that has a nice solution with SVD. And really, you should see this. I hope you see this roughly as AX is approximately equal to B. Okay, where this is kind of my B here. This is my A actually there, right? This is my X. Those are the decision variables. And the solution, the reason SVD is part of the solution, if I were to just solve the unconstrained problem, then we know that the solution should look like the pseudo-inverse, right? It should have that AA transpose business going around, and it does. If you take that solution, the picture I want you to have in your head is if you were to take that solution and then project it down to the closest rotation matrix. So projecting it onto the unit circle, SVD does that projection for you. Okay, so you build this data matrix, and I put it carefully in the notes. But you basically build this data matrix, which is the sum over the points of PSI on this side. You take an SVD of that matrix, you get something like U sigma V transpose, and you basically set this to the identity matrix, and that projects you back onto the unit circle. And there's a little trick to it too that that handles the rotor rotation case, the determinant equals +1 case. Now I have to admit, last time I said in order to solve this, you need to relax that constraint. I've actually changed my tune. I spent the weekend, thinking about these things, and there is actually a perfect optimal solution even in the case of rotation where you can adjust the singular values. So actually, some of the newest papers, and I think the right way to think about it, actually argue that there is a closed form solution to this using SVD. Okay, no relaxation necessary. You basically have to set the last singular value to 1 or -1 based on the determinant. Any questions about that? Now, I don't know if how many people actually looked at it, but I really want you to think about this graphically. So I'm forcing it into your browser right now. So you must comply. Oh no, it's a little bit too big for the browser, but this is theta, this slider on the left. And this green is the objective function, okay? As if it had no constraints, you would just do an optimization over that green. The red is the constraints, okay? This is the case. This is the special case of rotation matrices in 2D, parameterized with the two variables. My rotation matrix is parameterized by, I wanted to call it A and B. I plotted it. I named the plot A and B, but it made me, for plotting, I had to call this X and Y, okay? I picked a handful of points. You can make more points, it doesn't matter, a handful of model points. I rotated them to the scene points. I wrote my error, and I'm plotting that error function, exactly what we were just writing down. That's the green. Now, it happens that it has its minima, right? Like if there's no noise, then this quadratic function is trying to put all of the values of the matrix in a solution that is the right answer. Actually, the equality constraint isn't even needed. The best R in the whole family of 2x2 matrices there to describe the data is actually a rotation matrix. But in general, that's not true. If there's, like I say, if there's any noise in the data or whatever, it might try to shear or warp your object in order to match the data. And that rotation, this rotation matrix constraint brings it back down to the rotation matrices. That constraint looks like the unit disk in R2. That's what the determinant and the R transpose R constraint, they both actually have take the same shape, and it's the unit disk, okay? And the cool thing is, right, if you generate your points, your scene points with different thetas, it's just gonna walk right around there. And it's just, the beauty of optimization. Now the pictures are harder to draw in 3D, and they're going to be harder to draw still when we have outliers and other things happening, but I think the picture's almost the same. Now, and one of the ideas that I probably won't be able to say as well later as I could say with this picture on the screen is that one of the ways that we're going to relax the optimization later, in general, equality constraints, especially this non-convex equality constraint, being on the disk is a bad constraint. Because it's a non-convex constraint. The way you make that, you simplify that constraint is you fill in the disk. You say it's allowed to be anywhere inside the circle, and that would be a convex constraint. And when I say later that there's a semi-definite program that relaxes it, the basic idea you should have in your head is that it turns that unit circle constraint to a unit disk constraint. Okay, back to the whiteboard here. Now, and the rest, the second half of the ICP algorithm use closest points to determine the correspondences. I goofed. I was supposed to show you one more thing before I switch back. Sorry, to flip one more time. So I'm going to run a couple examples of the thing you're going to do in your breakout later, the same tool. But let me just show you the basic setup of sort of my toy problems that we're going to use to think about ICP. Okay, so there's a couple different variants of this all for you to play with, but basically I'm doing it all in the plane. Let me be super clear about what's happening here. The blue are the model points. I've always made some shape centered around 0. Okay. The red are the scene points. In the simple example here, I just, like in that notebook, that math animation, I just translated the model points by some, I applied some rigid transform to get them. And then if you play it, you can watch ICP doing its job. Okay. And you can step through. Okay, and I drew the correspondences that are being found by the closest distance metric as green lines. Okay, now remember we ask for every scene point to try to correspond to a model point, but we don't, there's no requirement that all the model points are used or that all the model points have a correspondence. Okay, so in fact, many of these points are corresponding to the same few model points as it starts. Things get better. It actually did not converge to the perfect solution in that particular case, but I have all kinds of variations of this here. So if you were to leave out the initial pose and run it, then it'll come up with a random initial pose. We can try it a bunch of times and sort of build up our intuition. And sometimes it's like super satisfying. It'll drag something from far away, lock it in, you know, it's really good. Even this one's kind of, it's not perfect, but it's actually pretty good. It, like I could probably still pick the block up if it did something like that. And then there's going to be other things that just make it, you know, really, really bad. Okay, so what are the different ways that we can make point clouds bad? And or, you know, I can make them bad here, but I'm trying to model things that like what might happen in the real world. So one of the things we could do is we can just say that the depth returns are actually a little messy. So I'll just add a little random noise to all the points. Okay, so let's see how that works. Okay, that was actually a lot of random noise for effect. So you know, these were originally perfectly distributed around the box, but every one of them got added with some randomness. And what do you think is going to happen there, right? In some sense, we're pretty robust to that, in the sense that we're solving a least squares optimization. So you'd expect that if you have sort of some sort of Gaussian type noise on the distance measurements, it's still going to try to find the least squares best fit. So actually, even though the point clouds are pretty messy, it's pretty good about that. I would actually say this is not the dominant problem in the game for a couple of reasons. First of all, our depth sensors have gotten really pretty accurate. I mean, they have lumps still, but you know, the measurements are actually fairly accurate when they get good returns. And because of this robustness of the least squares solution, it's, you know, I would say that's, you can run it a few times. I hope you will run it a few times during the breakout, but you know, maybe that's not the worst problem. How do I model outliers? Okay, so outliers, in reality, I told you, you know, you might get it from mist or like a bouncing reflection or something like this. You could actually, I mean, in cameras, you can actually literally see your own reflection and get some confusion there if the objects are shiny, right? You can also get outliers from having other objects in the scene. Like at the very least, there's going to be a table that's holding the object or a bin that's holding the object. And you're going to either have to subtract that out somehow which we can do, and if we know exactly the geometry, or you're going to have to, account for the fact that there might be some returns. Now, in this super toy example, I just added uniform. I just picked, you tell me a number of outliers. I'll just like look over that image and just drop a few extra red scene points uniformly distributed across the scene. So how do you think the system's going to respond to something like that? I mean, how robust would you be? I mean, it's pretty robust to the Gaussian noise around the objects. Well, let's see. Okay, so you see there's a few extra outliers. We're going to look at the equations to make sure we understand why this is, but they can be really, really bad. Okay. I mean, the quick version is that the error, the distance, which is what's contributing to the cost function for an outlier, can be much bigger in proportion to the many relatively small distances you get here, and it can really, really mess up your optimization. Okay, so outliers are, one of the things we really need a better solution for. There's also a notion of having only partial views. Remember, I could only see like half the mustard bottle, right? So to do that, I'll just set the number of viewable points to be some subset. There's, I don't know, 7 times 4 total points, 28 points in the total object. I'll just take the first 9 of them, I guess. See what happens there. Okay, so we're seeing, our cameras, let's say over here, it gets to see this side, but it doesn't get all the returns on the other side. How well do we think it's going to do there? This one's actually really interesting, and it's going to be the main thing I ask you to try to dig into a little bit on the breakouts. But let's see what this one does. Okay. So it converges to that. Okay, and you'll see in the breakouts, I even say, is least squares the right cost function? And I want you to play with it first, but then we'll talk about, I think this is a case where, it might be that it's really not the optimization's fault. It's sort of our fault. We kind of asked for the wrong thing. If you really just ask for the least squares objective to be minimized, it's doing a pretty good job. But if you want to pick up the object reliably, maybe not good. So I think that one's on us. Okay, and then you can, like I say, you can set deterministic yaws and positions and play with it. All good. Okay, so let me just talk a little bit more, and then I'll send you to breakouts to play with that. There's one other point that I didn't have a super simple way to make happen in the notebook. I kind of wish I had done it, but you never get the same points twice, right? So there's a few other we didn't talk about dropouts there, but those are very real. And so, but maybe they're not, I mean, if you just are missing, you just have less scene points to work with, maybe it's at least not going to screw up the scene points I do have, right? And since I'm only trying to correspond the scene points I have, maybe it's sort of okay if we're just missing a few scene points. That would be, the way I might model that would be just go through the scene points and randomly just remove a handful of them. Or if I was really clever, I would try to remove the ones right on the edges or something like that to replicate reality. And there are ways to simulate depth dropouts with higher fidelity, but it's, so there's a physics-based explanation for most of them. Dropouts and missed returns, Right, for instance, if you put a mirror in the scene, you're gonna get no returns. Okay, but the other one is that I never get the same points twice. So it sort of bugs me that I did exactly what the computer graphics people did in that toy notebook. I kind of did the same thing I accused the graphics people of doing, which is take your perfect point cloud, rotate it and then try to match it back, right? Because the real, that just doesn't happen in for robots, right? So for robots, I've got some object, I've got some, some points that I get on the object from the first time I looked at it, right? Let's say I'm looking at it from here and I get those sort of points on the object. If the object moves just a little bit or the camera moves or anything, then the next time I take a look at it, I'm going to get maybe very similar points, but I'm not going to get exactly the same points. It's whatever happens to line up with the discretization of my pixel space on the objects, right? So getting to zero error is just kind of not a thing in real robotics. But it is a thing in the beauty of sort of the experiments we're doing in numerically right now. Okay, so how do we detect outliers? Because I showed you already a little bit that they're bad, but I want you to think about them when we go into the breakout. So right, so once we have an estimate, detecting the outliers is relatively easy, right? Why? Because my cost function, remember, it even has a nice geometric interpretation, right? But each one of those terms is a squared distance. So the points that if I were to drop an outlier into this picture and I fit my pose to something that close to this box, the distance between the outlier and its closest corresponding point is going to be large. Right, so at first blush, points with a large distance are the outliers. The problem is you get into this chicken and the egg problem of you need a good pose estimate in order to have a sense for which one are the outliers. And you need, if you need the outliers, get rid of the outliers to get a good estimate of the pose, right? So how do you actually do it before, how do you break that cycle? There's a couple ideas out there for it. One of them is ransack, which we're going to have you explore in this stands for random sample consensus. And it's a pretty simple idea. And we're going to have you explore it in one of the problem sets. But the idea just in words is just grab a small number of points at random and do a fit based on that. And then you can ask how many of the remaining points are well described by that, or have a small distance. We distinguish between the inliers and the outliers. And if you just do that a handful of times, like pick 100 random small subsets of the point cloud, and then for each of them, you do a quick fit. And at the end, the one you say is the one I'm going to go with is the one that described the most points, in the sense that I got the most inliers, right? The ones that are not outliers are the inliers, right? Okay, so that's pretty good. And people still use you still see ransack all the time in modern geometry libraries. Okay, it's got like there's every once in a while you'll hit a computer vision paper that has like 20 times more citations than any robotics paper ever will ever obtain, and that's one of them. That one's got like, I don't know, ridiculous numbers of citations. It's been very impactful. There's another idea that I think is just very, very cool that I want to get across to you. And it's kind of builds on that notion of the trick of separating translation from rotation, right? The idea that relative positions were invariant to translation, right? Can we do something again that's actually invariant to both translations and rotations, right? So can we write something, an objective that is invariant to pose, to translations and rotations? And the trick to to be invariant to positions was to do the relative positions. Okay. The trick to being invariant to both of them is you write the pairwise distances. We already got halfway there with the picture I drew above to say that it would only depend on rotations. But if you throw away the direction of those relative transforms, relative positions, and you just keep their length, then actually that's something you can get information about before you even have any pose estimate of the object. Okay, the pairwise distances between points. You can give me 2 point clouds, they're not registered, and they both have pairwise distances between points that can be compared immediately. Okay, so that means if I take some points and I find out that their pairwise distance in the scene points is very dissimilar than any pairwise distance I have in my model points, one of those 2 points is an outlier. Okay. If distance between I and j in scene points is dissimilar to all dij in my model points, then either I or j is an outlier.
Or both.
Or both, yes. And actually, that's not crazy. I mean, so the picture I drew was like you've got 27 nice, beautiful model scene points, and then you have 3 outliers. But actually, if you're looking at a cluttered scene and you just want to pick up one little object, it could be that the bulk of your points in your scene might actually be outliers. And that's a pretty different regime to live in, but you could address it with this kind of a thinking. So what does that look like? It's actually really interesting to think about how powerful that observation is, right? So let's say I have my model. It's a rectangle or something like this. So what are the distances? What are my pairwise distances of my model look like? I mean, some of them are pretty small, right? So dij for the model, it's in some, I don't know, pretty small number. And the biggest ones, I guess, are this distance here, right? This would be max dij. That means, so, I can't rule out all points, but there's some set of points that if I were to take that and sort of add that to my object, right? Do you understand the picture I'm trying to draw here, where this is max dij, the length of each of these? Again. So if I get a point that's like out here, I can rule it out instantly. Or if I correspond the the distance between this and this, for instance, is dissimilar to anything I'll ever see in my model. So I can immediately say that one of those two has to be an outlier. Now the power increases a bit if you start saying, now I label a whole bunch of pairwise distances as either being outliers or not. And if you were, if you had all the time in the world, then the thing you should do would be then to find the maximum clique. So this makes a graph of points, of pairwise distance points. I'm just going to say this quickly. I know I'm not giving you enough if you haven't thought about these things, but I'm just going to write the basic idea. So if you make a graph where every scene point is a node in the graph, and you write an edge with its pairwise distance, and then you label the edges as either being inliers or outliers based on whether they're feasible, then your object has to not only be, contain points that are by themselves not outliers, but it has to make a whole set of points, which would be a clique in the graph. Okay, that's an expensive computation, but it's a cool computation, and I think it's worth exploring more. That came up in, I saw that for the first time in an algorithm called Teaser by Luca Carlone and company and Heng who are at MIT. So I think that, those kind of heuristics can be very good in the, I've got a huge, I'm taking a point cloud of my entire room and I'm just trying to find the coffee mug, but maybe they're not super good for two coffee mugs that are right next to each other. But I think their power is still being understood. Okay, so there's a couple more, I think, fundamental approaches to outliers, but I want to take this time now to do the breakout. I'm going to send you the breakout. I want you to just play with it and make sure that those kind of ideas are sinking in, and that you feel like you understand the role of noise, outliers, viewable points. I also made it so you can do random objects versus rectangular objects. So please go ahead and go to the breakout. I have a link to the questions right above this, and here's a set of questions to guide you. And I'll put that up on my slide here too, if you want to link on it there. Okay, so the question, just as we were coming back, was why are we always trying to match every scene point to a model point? For instance, could we do the opposite? And the answer is yes, it's trivial to do the opposite. You could just flip, you would put the rotation, for instance, on the other side, but similarly, you could just do it. It'd be equivalent to doing it in the model frame instead of in the world frame. Totally fine to do the other direction. But I think in both cases, they're wanting. I think we need to generalize our notion of correspondences, and that's exactly what we're going to do next, which is to be able to say some model points correspond to some scene points, maybe they correspond to multiple scene points, and we just need a richer representation of correspondences than what ICP gives us. But let me quickly try to make sure people saw that, they saw that local minima with the box, right? Because all of the points along the top were corresponding fairly well to the wrong point often, and it would have taken a lot for those 2 points on the side to actually pull you out of that local minima. Now, that's a case where I was saying it's kind of our fault. That's a modeling problem. I think least squares is not the right objective for that. If you're saying that all the points, at least where you're weighting all the points the same, and that's a real issue. If you're trying to pick up a thin book from the table, that's exactly what happens. A human, if you showed the point cloud only, the grayscale point cloud of a book on a table, and you showed a bunch of points on the cover and a few points on the side, those points on the side would draw your attention. You would not accidentally put the book somehow translated by 3 centimeters just because it fits a lot of the points on the top really well, right? Somehow there's extra information there that the least squares objective doesn't capture. So I think that's a really good thing to continue thinking about. Is that as much as the math is beautiful, it's not clear that these are exactly the right objectives. What else did people come away with from that the breakout? Did anybody else have any other ahas or questions? Did you find other local minima? Yeah, and Dale is shaking his head yes. I mean, you could flip it upside down. You might have to get a little dramatic with your.
Depending on where you set it up, sometimes it'll be offset by 1 point over compared to the minima you set up, or things like that.
Really?
Or,
you can get it. You can get it 2 over.
Yeah,
I hadn't seen that one. That's good. It makes sense. I mean, once you have the wrong correspondences, you have to do something. You have to go up in cost to get the right correspondences again, and just having a few off to the side isn't enough.
Basically, if you just start it way to the left, then it snaps and jiggles a bit and eventually stalls.
Yeah. Cool. Good. Okay, so let's generalize our notion of correspondences a little bit. So like we just said, right now we've been going from scene to model points. You can imagine just removing scene points. That gets us a little bit farther, right? So if I just, let's say, if I just, allow somehow that that not all scene points correspond to a model point, that already gets me something better. And actually that gets you pretty far if you were to do that, because now you can have both the subsets in both directions. But that's still a little bit restrictive, and it's maybe a slightly harder formulation. Well, there's times where that's a good formulation. But let me just rewrite it in a slightly different way, in a way that I think is going to generalize better. So if we were to instead write our objective as minimize x over SE3, we're going to do our x. Let me just do I, not CI. I'm sorry, I'm going to use J on this one and I on this one. I'm going to do a sum over both I and J over here. And I'll just put a bigger C matrix, a matrix of correspondences, okay, where Cij is now a 0, 1 matrix, which has got N, it's, which way do I want it? NS by NM point entries, okay. This actually, if you were to go through and set the values to be 1 exactly where Cij in our previous ICP approach worked and 0 everywhere else, then this can perfectly represent the thing we've already done. You agree? That this thing here just being 0, 1 will keep the terms which had correspondences and remove the terms that don't. So that's an equivalent optimization, but you can imagine it's a more general one, where now if I don't have a constraint that Cij has only 1 element per row or column, then I'm allowed to have multiple model points or no model points or anything like this. Okay. Now, there's another important algorithm to know, which is called coherent point drift. So and it uses this version of correspondences, but it actually uses them in a way that is soft. Okay, so you're allowed to, instead of taking, now I'm going to take Cij to be in anywhere in 0 and 1. Okay. And you're allowed to have multiple weighted combinations of different particles that are corresponding or not. Okay. Now, if you read the CPD literature and all the things that go around it, you're going to see Gaussian mixture models. You're going to see lots of language. It's got a probabilistic interpretation, which is good and useful. But I swear it's exactly just doing the thing we know and love. Even though they write it as Gaussians and maximizing log likelihood, if you take the log likelihood of a Gaussian, you just get back to a quadratic form. It's the same math, just hidden in Gaussians and pictures. Okay, so, but the nice thing about the probabilistic interpretation is that you can think of this as a probability of scene I corresponding to model J. And then it gives a kind of a natural way to think about what the weights what you might want to use for the weights. So you can set the weights based on these Gaussians. So you think of a Gaussian kernel around there, you get a scaling function like this, then e to the -1/2, all my Gaussian terms, right? Where this is x PMI minus PSI or PIJ or sigma squared, okay, a Gaussian. And the picture you should have in your head now is that I have my model. And I have my scene points, but all the scene points, wherever they are, I'm going to score them based on kind of a Gaussian kernel. So every one of these model points says I've got some probability of explaining the data as I go away. So this is going to still be the case where I'm going to alternate between setting Cij. So I'm going to set Cij according to this rule, which is my Gaussian kernels. And then for Cij, I'll optimize X. I'm answering the question, sorry if I didn't give the context. I'm going to optimize X, and then I'm going to refine my weights Cij, and it's going to be an iterative algorithm just like ICP, but a softer correspondence model and a more general correspondence model where things can correspond with many points. Okay. It also has a nice interpretation. So first of all, what does it do for outliers, right? So the points that are far away sort of naturally fall, if I have my distances large, they're going to be in the tail of the distribution, so they have very small weights. So it handles the Gaussian kernel, does the right thing for outliers for us. Okay. There's also a way to set, if you include in your normalization constant some slop term for just outliers, then you can ask for all of your correspondences that do match to sum up to less than 1 and leave that residual probability to capture the fact that I expect things, in a Bayesian sense. I have a prior that some number of points are not corresponding. So it's a flexible framework and just a slight generalization over ICP. And the magical thing is that the pose estimation step we did before is basically, it's identical. So we do a weighted version of the data matrix and a weighted version of the central points because they're scored according to these weights, but otherwise the math just goes right through.
There's a couple questions on the chat.
Okay, good. How does optimizing work in the non-CPD case if it's not a continuous function? Sorry, so Alex, say that again, maybe even with Mike.
Sorry, maybe I didn't write that correctly. So I understand how optimizing over Cij would work in the CPD case, because it's like you go from 0 to 1 and like find points in between that. But if you're locked into either 0 or 1, how do you optimize Cij?
Okay, so just to be clear, even in the CPD case, we are not optimizing Cij. We're assigning it based on, this is the equivalent to the closest point set, where in the closest point in iteration, we would just assign Cij to be the closest point. I mean, you could say it's optimizing by that closest point metric. This one is actually just assigning by going through and summing across the Gaussian kernels. Now that is the big question you just said is now how do I, if I were, the dream is that we would be able to, in a single pass, optimize both our pose estimate and our correspondences. Okay, and there is some cases of being able to optimize Cij and X jointly. Okay, so let me try to tell you about that special case. The way that people typically would write that actually is they would change away from the Gaussian kernel to a truncated least squares. So you get back to the land of quadratics, but you clip your quadratics. So think about your kernel function as being my quadratic function that we know and love, but it's clipped off at 0 here. Actually, we're gonna turn it upside down and minimize it, but that's the same picture. So the difference between the Gaussian and this, you kind of squint, it's okay. And this one is actually gonna be potentially more amenable to optimization. The reason it is in the extreme case, you can write down these, well, let's see, I'll maybe actually give you the real answer here. So optimizing truncated least squares, TLS, for positions is relatively easy, because that's a truncated least squares on a scalar case, because you can actually even optimize X, Y, and Z all independently. And the scalar case of a truncated least squares problem happens to be a good case where we have a nice solution. Okay, optimizing it for rotations, yikes. But it can be done. Okay, actually the teaser algorithm in that family, again, they write, well, so we did a version of it in my group, writing it as a mixed integer program, which will find the right solution, but it might take a long time. So it actually, it has its uses if you're trying to solve something. There are times where the timescale doesn't matter, and you can spend a few minutes trying to find your points. Sometimes it's way more than a few minutes, but there's a formulation of it as a mixed integer program. Teaser took it a step further, and they write a SDP relaxation, semi-definite programming. So that's a semi-definite. Also very expensive, but way better than the MIP. And that is one of the cases where, first of all, it's turning that unit circle constraint into a unit disk constraint. And it has to do the same thing for the binary variables that we would get to handle this clipping. Okay. And the statements that you can make for a problem like that is not, you cannot guarantee will always, the relaxation is not necessarily tight. So basically, if you solve this hard problem, the good news is you can check to see if it got the right solution. So you can check your constraints at the end and see if the solution to my relaxed problem actually gave me something that was on the unit circle, for example. Right? If I turned that unit circle constraint into a unit disk, you can imagine in the graphic that we played with before, if the bowl was outside, then it would be optimal. It'll pull it back to the inside. Or if it had the no noise case, it would be exactly on the circle, and the relaxation is tight. If it sneaks inside the circle, the unit disk is not going to be a tight solution, but you can at least check after the fact. So Teaser recommends you solve this big SDP. If you get a good solution, you're certified that you've got an optimal solution, globally optimal solution. But in general, there's no guarantees you're going to get that. Well, I ran out of time, but that was a really good question. Yeah, that's a good, I think we got, so those were the big ideas, right? So point clouds are messy. There are explicit ways to identify the outliers in particular. Those are the particular focus for today. You can identify them, you can pull them out. You can generalize your notion of correspondence to be the soft correspondences in CPD. And there is actually, I'll write up the truncated least squares version in the notes too, because I think that's a good idea. Any last questions? All right. I'll see you Thursday.
Thank you.
Sure, thank you.
Thank you.
Thanks.
Thanks.
Thanks. I actually had one last question.
Go for it.
So when humans do, or like when humans try to pick up an object, is what they're doing like something like the optimization problems here, just implicitly in their head?
So I did put this at the bottom of the notes, but so I'm embarrassed that we're not using the color channels yet. And I think humans, like if you ask us now, my students now, like if you were to give up RGB or give up depth, they would give up depth and just go purely based on color these days. I think color is such a strong cue that I haven't talked about in these algorithms because it's hard. It's hard. I mean, the distance, like how do you compare two color values? If there's a shadow or something on the object, it's the same object, the color value's changed a lot. It's very, very hard to do that. Deep learning really helped us with that. So I think probably humans aren't doing what this is doing, and this is, but robots also have, I think, superhuman sensors. And if you have really the ability to measure distance super accurately in a huge point cloud at high frame rate, then you shouldn't be doing what humans are doing. You can do better for some measurements. So the art will be in the next few years combining them in better and better ways. We're already combining them fairly well, but take advantage of those sensors if you've got them.
Got it. Thanks.
Cool. Long answer to short question.
I had a small question as well.
Sure.
So it kind of relates to what we talked about today, but not really. So just because I saw a couple of weeks ago that I think your group like just published something about correspondences in more semantic areas, with like this visual descriptors. I was wondering if coherent, so point drift could be used there, where like the semantic, like I don't know, like the visual descriptors are in space as well, and then you have that transformation and also the assignment matrix. You can like both optimizations.
Totally. Well, the way I would think about it is, so that work you saw was a deep learning. It was learning correspondences with self-supervision, and so it's a deep network that basically says, do these two things correspond? I mean, it's a deep network predicting some intermediate value, and then you can check correspondences in the intermediate value. I would say the way that would obviously snap into what we just said is that you let the deep network populate C. Mm-hmm. Right? And then I think you could fly through this. And we did it when the dense object nets paper came out. We showed that we could do it for ICP. We didn't actually do the CPD version of it, but we just did the maximum, the closest point in a metric, which was induced by the dense object nets. Yeah, I think that's a great connection.
Awesome. Yeah, because I was just thinking maybe C is wrong, maybe the descriptors are not good enough, and then anyway, thank you.
You're spot on. Yeah.
If you have, so we've been talking about kind of like matching a known model. I guess like under the guise of that we know the model corresponding to the object we're picking up. If we instead had like maybe like some prior belief over a set of different models, how do you go about like designing ICP to kind of figure out which object you're trying to grab in the first place while also aligning the model with the scene?
Good. So the estimation actually gets easier if it's just an affine transformation instead of a rigid transformation. So what that would look like would be you're allowed to stretch or scale your objects. Then most of the stuff we did today, if it was just like small mugs of this shape or big mugs of this shape, that part's easy and snaps right in. If you go to like a more general notion of object, like all the different mugs you might find at Starbucks or something, then that doesn't work well. And that's actually one of the things that motivated the work that Uri, was it Uri? Yeah, just was asking about, is trying to find representations of objects that are more general. We're going to talk a little bit on Thursday even about some of the sign distance function representations. And I think one of the new trends these days is to try to not use meshes anymore, but actually to learn sign distance functions. That seems to be a nice representation. So I'll show some of that stuff on Thursday. But I think even for geometry, so that would be in the case of just trying to model classes of geometry. But geometry is not the whole story, right? So there's a lot of semantic information about objects. There's temperature, there's whatever, there's, you know, all kinds of information that you could be using. And the geometry is the one, it's like a siren song to try to like think more about the geometry, because there's like good answers often, but I don't think it's the whole story. So we have to remember about all the other cues, RGB, for instance.
Thanks.
Sure. Okay, I have to run today, but thank you for all the questions, everybody.
Thank you.